Okay, so I'm talking about nextpnr, or next open source place and route tool for FPGAs. So to give you a quick overview over free and open source FPGA place and route tools. So probably this list is incomplete, but I think these are the most important projects for this discussion. There is VPR, which is over 20 years old. It has good, stable, timing-driven algorithms. It's pretty portable from one architecture to another. All you need to do is write an architecture XML file describing the target architecture. And this makes it very interesting for stuff like architecture exploration, because it's very easy to change things in your architecture. But at the same time, it's not really the best solution for doing place and route for actually existing real-world FPGAs, because there it's not sufficient to have something that is pretty close to the real thing in terms of routability and stuff like that, which is absolutely fine if you do architectural exploration and algorithms research. But if you would like to actually generate a bit stream for a real-world part, you need to have an exact description of what this thing looks like. So with VPR, it's easy to get close to actual hardware with the architecture that you're describing, but it's surprisingly hard to actually get to the real thing. So when we originally did the ICE40 with Project IceStorm, we wrote our own place and route tool in 2015 called arachne-pnr. It's not timing driven, it only supports the ICE40 FPGA, but it was good enough for many people, and we have a lot of users. But now we are expanding and going to support more devices and probably more interesting applications. And we decided not to just keep hacking on with arachne-pnr and add more and more things and make it some kind of Frankenstein's place and route tool. But instead, we decided to start a new project where we have portability to different architectures and stuff like that in mind. And that new thing is called nextpnr. So it's timing driven, but of course it is relatively new. So we still have some things to do to get to maybe the state of how good of algorithms we would like to have here. It's portable, so it supports different architectures. You can take nextpnr, and by adding the appropriate code, you can add support for a different architecture. And it's a team effort. So I'm kind of known for this kind of lone wolf projects, but this is not it. So there are a couple of people working on this in different areas, which is also, for me, a very interesting and new experience for how to make projects. It has also a GUI, which is also a new thing for the kind of projects I usually do. But I really like our GUI. I will show you a screenshot on the next slide. But don't worry, it still works very well with makefiles, because yeah, in many cases, I think that's the kind of approach that is actually most easy to manage. So I said it's portable. The way we do this is there is a API between the core nextpnr algorithms and your architecture description. And if you would like to add a different architecture, you just have to implement this same API, and then the rest of nextpnr will be able to work with this description. So that also means we essentially create different executables for different architectures. So you compile nextpnr for ICE40, and then you get a nextpnr-ICE40. Or you compile nextpnr for ECP5, and you get a nextpnr-ECP5. They share a lot of code, but it also means that when one architecture has a certain feature and that other architecture doesn't have that other architecture can just, for example, return 0 in an inline function, and the compiler will get rid of parts of the algorithms that are not necessary for this architecture in question. So currently we have two architectures that seem to work quite well. One is ICE40, the other one is ECP5. The architectures that are currently planned or under construction is a generic architecture that would allow you to essentially build the routing graph and stuff like that from your Python script. So that can also be used for stuff like prototyping and maybe even exploring architectures. We have a branch that you can't see at the moment, but we will probably either release it in some way or merge it to the main line that supports Torque, which is a framework for doing bit manipulation for older Xilinx devices. And of course, we would like to add support for Xilinx 7 series devices because we've documented the Xilinx 7 series bitstream. So now we actually want to do place and route for that. Further plans feature-wise, so these are things that we want to support in the near future, is floor planning, is designs with multi-clock constraints where you have different clock domains, and other kind of complex constraints. So some of the things already work in one way or the other. So we have already something for things like relative placement constraints that works quite well. So you can see from this feature list, what we are aiming here is something that can actually replace many of the more traditional tools, even in complex designs with complex requirements. This is what we are aiming for. Okay, so this is a screenshot. Actually, it's an older screenshot, but I didn't have the time to create a new screenshot because it actually takes some time to add all those colors to wires. But you can actually see the device, you can see where the nets are routed, where they are placed. You can investigate the design netlist and see where was something placed. And of course, ultimately, we also want to support things like entering floor plan constraints via just drawing boxes in this graphical user interface. And what you can see in the lower left corner here is the Python console. So all the internal nextpnr APIs are exposed to Python, and we decided we are not going to bother with implementing a Tickle API, instead we just use Python. So sorry if anyone here is really enthusiastic about Tickle. So the coarse nextpnr architecture looks a little bit like that. So we have a couple of algorithms. This can be common algorithms that just generic place, generic router. Some algorithms are architecture specific. For example, packing is usually something where you would like to write a little piece of code for each architecture that knows how to pack for this target architecture. Or another thing would be bitstream generation, because that's also fairly architecture specific. So those algorithms, they talk to the design database, the placement database, the routing database. These are in-memory databases that essentially, so the design database is just the netlist, where you have your nets and your cell, and the placement database just assigns the cells to primitives on the device physically, and the routing database just takes a net from the netlist and assigns it to wires and programmable interconnect points. So the algorithms are talking to these databases, but they're also talking to the architecture API that abstracts away the concrete architecture. And you can see here in this graphics, I have a couple of different instantiations of this architecture API, because we might have different architectures, of course, that's the whole point. And then those architecture APIs, or the functions behind these APIs, will then access the actual architecture database. And again, you can see we have even more architecture databases than we have implementations of the API, because, for example, for ICE40, we have one implementation of this architecture API, but then for each device in the ICE40 series, we have another database file. Okay, a little bit nomenclature. I'm not going to use a lot of these things in later slides. It's not a very in-depth presentation, but I think this helps understanding what kind of elements we manage in those databases. So in the design databases, we have cells, and those cells, of course, have ports. It's a netlist, so we also have nets, and then we have somewhere list that says which net is connected to which port on which cells. And for each of those, so we call them sources and sinks, where the signals come from and where they're going to from the net. And a pair of source and sinks, we call that arc within nextpnr. And you see here already a big problem with naming things in an industry like that, because in ECP5, as you have heard in David's presentation, they also use the term arc, but they use the term arc for something that we call programmable interconnect point. When you're talking about different stuff and when you're integrating the nextpnr layer with the architecture-specific layer, sometimes you have to keep in the back of your mind if you're in the domain where this nomenclature is used or the domain where that nomenclature is used. Otherwise, you get confused. Okay, so that's the that's essentially generic. So no matter what architecture you are targeting, you will always find a design database that manages this kind of objects, and it's always the same implementation. But on the architecture side, we have a database that manages this size, this list of objects, these objects here are stored in a different form for each implementation. So nextpnr itself only has a view to this database through the architecture API, but the architecture can implement that either way. So what kind of objects do we have in the architecture database? We have bells, so that's a basic element. And essentially when you place a cell, what you do is you assign a bell to that cell. So placement is just finding a mapping between cells and bells. That makes sense. And of course we have things where you connect to on the bells, and we call them pins, so there are no confusions with the ports on cells. We have pips, which is a programmable interconnect point, which just says this source wire and this destination wire on this chip. When this pip is active, then there will be a connection. Pips are always unidirectional, so if you have a bidirectional pip in your actual architecture, you have to represent it as two anti-parallel pips in this API. And for the router, there is no concept such a bidirectional pip. It's just two anti-parallel pips, and it decides which one to activate depending on in which direction it routes a net over a bidirectional wire. Okay, a wire is just a physical wire in the chip. And an alias is a special pip that connects two wires, but this pip is always on. And the idea here is that in some cases, you have a tile here on your chip and a tile there on your chip, and you have a wire and a wire. They have different names, but it happens to be on the chip to actually be the same like routing node. And the way that we express this in nextpnr is that we add a special pip that is automatically activated whenever we route to the source wire of this special pip. And then we have groups, and groups are not used by any of the algorithms. They are more for the user interface, and they're just collections of bells and pips and wires or other groups. So if you have a structure on your chip, like there is a tile and the tile contains slices and stuff like that, then you can represent this structure using this group mechanism. And this is primarily used for displaying information to the user about where a resource is and stuff like that. Okay, so now you have a basic idea of what this architecture description does. So how do you add a new architecture to nextpnr? And you essentially go through these steps here. You add a new top-level directory in the source repository for your architecture. You add a little bit of CMake magic to make your architecture exist in the nextpnr build system. And in this architecture directory, you will then have to add two additional files. One is archdefs.h, where you define data types used by your architecture. So there are a couple of data types, like a wire ID or a bell ID, that are architecture specific. So for one architecture, a wire might just be identified by an integer that points to some entry in a database. In another architecture, a wire might be identified by a pair of x and y coordinates identifying the tile, and then an integer that is an index in a per tile list of wires, for example. So each architecture can choose whatever fits the architecture best and just adds those implementations of those types there, and then the rest of nextpnr on compilation will use the appropriate types. And then arch.h is where you actually create the interface. This is where you add the API. There is an arch class that you have to implement in your arch.h, and that has about 100 methods that need to be implemented for a complete architecture. Yeah, and then you add a couple of C++ files with the main function for your architecture. So right now the main function is something architecture specific because each architecture might have different options for different input and output formats that make sense for this architecture but not another. Yes, and also C++ files for the architecture-specific algorithms like packers. When you're going through that process, you might start without actually having a packer, and then you have to instantiate the actual placement primitives in your HDL code, and then you can see if the other stuff works correctly, and when the other stuff works correctly, then it's a good time to start actually implementing your own packer. So we're still a little bit in the process of finalizing this architecture API. The changes we do right now are small changes. It's not like complete rewrites or something like that. But we would like to add like architecture slowly, one at a time, because with each new architecture we add, we discover new things that might be useful to have, or that it might be useful to solve this issue differently in the architecture API. If you want to implement an architecture, please do so, but do so one at a time, not an avalanche of architectures, because when we add 100 architectures at once, then it will be very hard to make these small improvements in the API. Okay, 100 methods, that sounds like a lot, but it's actually not that that's scary when you look at it more closely, because those methods are very, very fine-grained. There is no give me all the information about this bell API call, for example. Instead, we have one function that gives me the a bell based on the name of a bell, and then another one that takes a bell and produces the name for that bell. And another one that gives me the location of a bell. And another one that gives me a bell by the location. And so you can see, because these are very, very fine-grained functions that each just query one information about a thing. Because of that, we have 100 methods to express the entire architecture. Okay, so you would like to add such an architecture. And I've guided you to the steps of what kind of functions do you need to implement and stuff like that. I gave you a course overview. But what about the more abstract, like higher level strategy for doing that? As far as I can see, there are 3 noteworthy strategies how you can build your own architecture backend for nextpnr. The first one is just having a flat database, and that's what ICE40 is doing. So that means for each wire, for each pip, and for each bell in your device, there is one explicit database entry. And if your chip is twice as large, you have a twice as large database. And that's fine for ICE40, because ICE40 doesn't have huge parts. But when you go to larger parts, like for example ECP5, then this can become a problem. And also it's kind of wasteful, because when you look at the structure in more detail, it's just the same thing repeated over and over again. So why do we need to unroll all this and create a huge database? It would be much easier to have something like a deduplicated database. With a deduplicated database, the approach is we first generate a flat database, but after we have generated the flat database, we analyze it to find things that are completely the same, and then we can deduplicate it and say, okay, there is only one blob in the database for this kind of tile, and then a couple of references that say, oh, this tile and this tile and this tile, they all fall in the same category at that one. And this way you can drastically reduce the size requirements for your database, of course. It's still not going to scale forever because you have this intermediate step where you first have to generate a flat database before you deduplicate it. The last approach is to have a tile-based database where we don't first generate a flat database and then analyze it to get rid of the duplication. Instead, we just describe the chip in terms of this is the description for one tile, and now we instantiate it a couple of times. And this is the strategy that we are planning, or that I am planning for the Xilinx 7 series architecture backends. One big advantage of that is that you can easily support a whole family of chips with just one database, because the whole family of chips, they just use the same tile. They just instantiate the same tile in different grid sizes and maybe different patterns of what types of columns are used in which order. Okay, so the idea is that in the end, when we have Xilinx 7 series support, we will actually have example implementations of all those three possibilities. And then when you add your own architecture, maybe you don't actually start from scratch with an empty archdefs.h and an empty arch.h. Instead, you just copy one of the architectures that is closest to the requirements that you have for your architecture, and then make the necessary modifications and adaptations. Okay, the next steps for the project, we're trying to slowly replace arachne-pnr as IceStorm place and route tool. We are pretty consistently generating better results with nextpnr than with arachne-pnr, but there are a lot of happy arachne-pnr users. We don't want to startle anyone, so we would like to have the people who would probably benefit from nextpnr or who are most happy to experiment with new stuff as early adopters, so that when the whole bulk of users is going to migrate to nextpnr, they are not going to encounter stupid bugs. So we have long to-do lists for the improvements that we would like to do in the placer and in the router. And one hope is that in addition to being an open source place and route tool that targets actual devices, we would like to provide an attractive framework for algorithms research as well. And I think the main advantage here is that we can actually target real-world devices, and I think it's a much more convincing argument if you have a new algorithm that you can demonstrate the usefulness of your algorithm on a real-world device and not just a made-up device. Okay, and of course support for more architectures, and then at one point world domination. One thing here is, because we have this very flexible architecture, we would hope to be able to also write architecture backends for maybe some commercial silicon that we do not need to document ourselves. If you have maybe your own company FPGA or whatever, and you're not happy with whatever place and route tool you're using, then please reach out. Yeah, so arachne-pnr is producing consistently better results than nextpnr is producing better results than arachne-pnr consistently. That's what you see on the left side. On the right side, you see that the nextpnr runtime is a little bit worse compared to arachne-pnr, which might in part be because we use more complex algorithms because they are now timing-based. So maybe at one point I will also make a comparison where I disable the timing-driven stuff in nextpnr, and then we can see how they compare performance-wise. Okay, two quick announcements from my side. The one is at date next year, we will have a workshop, a Friday workshop on open source design optimization. We call it OSTA. And the topics, they include things like open source tools, so stuff like that, and IP cores, open source IP cores, maybe new languages and methodologies, stuff like that. So if you are going to be at date and you maybe interested in open source, then please attend the workshop. If you would like to present, please go to oster.gitlab.io. We just got the confirmation like last week or so, so we don't have a lot of information yet on the website. I think we don't have a deadline yet for submitting papers, so please check it in a week maybe again. And another thing that we are trying to do is we have this new icebreaker FPGA board. I know there are a lot of FPGA boards out there, but we are very, very confident that this is actually a very, very good learning platform. And because I'm running out of time, I'm just asking you to talk to me personally afterwards if you're interested in any of that stuff. Okay, do I have time for questions?
Questions? No questions?
Are there any timelines for Hello? Okay. So are there any timelines for Are you sure? Are there
Maybe just yell it and I repeat it.
So are there timelines for the world domination?
Oh, yeah. It's secret.
So if there's no other question, Julius.
All right. What do the tool vendors think about this? Do they talk to you at all?
It's a very difficult question, in part because the tool vendors are very, very large companies, and there are very different voices within those companies. So depending on who we talk to, we get very enthusiastic reactions or close to hostile reactions. There are a couple of stories that I can share, maybe over a beer, but I think I'll just leave it at that answer yet.
Do you think you're hurting their business or helping?
Well, so especially with FPGAs, most of the tools come directly from the FPGA vendor. There are very few third-party tools. And the third-party tools usually have the claim that they produce even better results than the vendor tools. And right now, we are lagging behind the vendor tools a little bit. So I think the commercial use case for actually selling like licenses is for the other end of the spectrum right now. So I don't think that they are afraid yet. I think in terms of commercial impact, this might be very interesting for the device vendors because they don't need to invest that much time in building their own tools, but I don't think that this is any danger yet for the people who sell tools on top of what the device vendors do.
Are you worried about them being concerned that you're documenting their internals? And releasing essentially, a model which represents what is going on inside their silicon?
Only a little bit. So I'm not a lawyer. I don't want you to go into like legal arguments here. Yeah. But let's say one aspect is that being in Europe helps.
Sure. So I think it's great. I think it's kind of bullshit that these guys think that, if our internal architecture, or at least how it's programmed, is given away, then oh my god, that's our secret source. I think that's utter crap. Right?
Yeah. So so I've now documented 2 different FPGAs, and David has documented one, and John documented the Xilinx 2000 series. I can't talk for those other peoples, but I have not really learned deep insights about architectural details by documenting where is the bit that activates or deactivates a certain feature. So usually the vendors already provide very good documentation about those kind of things in their data sheet, and then it's pretty clear, okay, there must be a bit that enables that, and there must be a enum setting to get the PLL in that mode, and so forth. And I don't think that just the location where these bits are in the bit stream reveals that much secret information about how they make their chips.
Yeah. That's good work, mate. Keep it up.
Okay, let's thank the speaker again.
More questions?
Yeah, just to add to this, for routing, I mean, doing place and route timing driven, this reveals a lot of internals actually. So it's not just about the bit positions, but if you want to do timing driven, you have to know about delays and real timing about the features.
Yes, but so on ICE40, for example, they have in the datasheet a couple of reference timings. How long does it take from here to there, stuff like that. When you go to the Xilinx thing, so via the Tickle API, you can get a very fine-grained report about where does a signal spend time. So I would argue that a lot of that stuff is already documented in one form or another, just not really in a easy machine-readable format so that you can feed it in your own tool. But if they already put the information out there, just not in a convenient format, just converting that in a different format, I would say, does not really reveal anything that they haven't documented before. Hagen still has a question.
Can we maybe take it offline? We're running a bit. Well, maybe we can do it and we start setting up the next one already.
Sorry, I don't have a question. I have just an annotation. I think the business for the FPGA vendor is more on the part to say it's better to use lookup table with 5 entries than a lookup table with 6 entries. So the vendors looking how the usual designers writing code and which structure would fit the needs. So I think they have the secrets or the business stuff inside there, not in the wires.
So I think even there, through timing, you document a lot how the lookup table, for example, is built, because you can see. Okay, thank you.
Thank you.